Welcome to another podcast. In this episode, we're going to be taking a look at how to do reduction formulas via integration by parts. If you look in the lecture slides, there's an example of this using natural log. I want to do a different example here. The example that I have in mind for us to start with is to look at the integral of x to the n e to the x dx. And so I want to discover its reduction formula. And then I also want to use it to solve when n is 3. So that's what we're going to be interested in here. I want to look at the n equal to 3 case. Now, if I was to look at the n equal to 3 case right now without showing you this reduction formula trick, or without showing you tabular integration, which is another video, you would have to do the standard integration by parts at least 3 times in order to make this work. So that's pretty tedious, and so instead of doing that, what we'll do instead is sort of our standard first look at integration by parts, and then we'll use a recursion to make this a little bit better. So if I was asking you to do this via integration by parts, your substitution would be for the u, we want to reduce the power, so it would be x to the n here, n x to the n minus 1 here. I'm assuming in this case that n can be any value, even if any positive integer value. If it was something other than that, then we would have to adapt our rule a little bit to deal with the possibility of it ending up in the denominator. So for these problems, I am only looking at n greater than or equal to 0. That's all I'm considering here. And only for integer values of n greater than or equal to 0. So my du is nx to the n minus 1 dx. My dv is sort of the standard dv when e's involved, because it's so easy to anti-differentiate. And so here we have a good integration by parts substitution. Let's apply the formula. So this is equal to u times v minus the integral of v du. Alright, let me make one more small change here. I'm going to pull out this n and write it this way. And so what you see has happened is we've gone from having an n for the power in the integral to now this new integral has an n minus 1. We've reduced the power by 1. That's why we call this a reduction formula. Now, if we were actually trying to get this down to a point where we could integrate it, we would have to do n minus 1 more of these steps to get that down to being x to the 0, which we could then integrate e to the x, which would be the only thing that's left. We don't want to do that. Instead, I want to name these things. So I'm going to name this integral in of x. So it's the integral of order n of x, meaning that the power n corresponds to this. So if I'm looking at n equal to 3, then I3 would be x cubed e to the x. Question now is, what am I looking at over here? Well, if that is in, then this is x to the n, e to the x, minus n times, and if you look at this integral, this is n minus 1. So the basic recursion formula, so if I'm thinking about a recursion here, the recursive formula is in of x equals x to the n e to the x minus n minus 1 of x. So this is the thing that I want to clue in on. So anytime you have a recursive formula, together with that recursive formula you have a base case. The base case is the smallest case for which the formula will work. In this case, our base case corresponds to n equal to 0. So I need to figure out what is I0. I0 in this case is the integral of x to the 0 e to the x dx, and you always hope the base case is really easy to solve. In this case it is. This is just the integral of e to the x, which is e to the x plus a constant. And so we now have our base case as well. If you put those two things together, you can accomplish any higher order by starting with the base case and using the recursive formula to get the next one in line. So I said before that I really am interested in I3. And so since I'm interested in I3, let me sort of outline the process here that you would take to get to there. You start with the base case, which is e to the x plus c. Next up is I1, and according to our recursive formula, I1 is x to the 1 e to the x minus 1 times I n minus 1. If n is 1, it's I0 of x. But we already know what I0 is. I0 is e to the x. Now, understand that this c is not the same as this c. I'm combining constants here. We would technically get minus e to the x plus c, so I'd have a minus c, and then I'd have another integral there that would produce another integration constant, and so on and so forth. So I'm just going to have one constant c throughout all of these, but notice at each new step I'm recombining it with old constants. Alright, so keep going. I2 is x squared e to the x minus 2 I1. Well, what is I1? Well, we have it on the previous line. On the previous line, it is all of this. Okay, one more. I3, this is what we were interested in. I3 is x cubed e to the x minus 3 I2. So this would be x cubed e to the x minus 3. I2 is previous line. Got to keep all our parentheses straight here. There's going to be a lot of them. Plus a constant. And in this way, you could keep going up to any particular value of n that you're interested in and find the formula using this recursion. Some people will call this bootstrapping. So if you ever hear that term, the bootstrapping, it's basically pulling yourself up from a base case using a formula to get to the higher order ones. It's a very different way of thinking about it, because typically if I had asked you about the n equal to 3 case, you would start with x cubed, you would work down. Instead of working up to x cubed, you would work down to x squared, to x, and then finally to 1. And so it's a very, very different way of thinking about this process. The idea of a recursion is an extremely important theme in mathematics that not only do you see pop up here, but all sorts of computer science applications and discrete mathematics, as well as differential equations, difference equations. These things are all intimately related, and so it's a good thing for you to have seen some recursions early on in your math career, and this is a really good example of it. Alright, thank you for watching.